Okay, Risto, you start.
Sorry?
You start.
Are people already in? Yeah, I guess so. Yeah. Maybe I'll just wait a couple of minutes because I see some people are still coming in. Okay, I guess I'm going to start. Good afternoon, everybody. Welcome to the webinar organized by Electronic Structure, a new multidisciplinary journal from IOP Publishing. My name is Risto Nieminen and I'm hosting this webinar and also serving in the editorial board of the journal. I'm extremely pleased to introduce the webinar speaker, Professor Hugo Dill, who comes from Switzerland, where he is serving both at the EPFL in Lausanne and at the PSI in Villingen. A few words of Hugo. He's originally Dutch and took his master's degree in Delft Technical University in 2002. But before that, actually, he had studied a couple of years philosophy in the United States. So this was his start in his scientific career. He went to Germany to do his PhD, which he completed in 2006 under the supervision of Carsten Horn at Fritz Haber Institute and the Freie Universität in Berlin. The topic of the thesis was electron confinement in thin metal films. Since 2013, he has been a professor at EPFL and an adjunct professor at PSI in Villingen, and has quickly made a name in electron spectroscopy, especially in spin-orbit interaction-induced spin polarization as investigated by spectroscopy. He wrote a review article in Electronic Structure, which has attracted quite a lot of attention and has been read and downloaded a huge number of times, which has the same title as today's seminar, Spin and Angle Result Photoemission on Topological Materials. So once again, welcome everybody and welcome Hugo, and I give the word now to Hugo. We have the possibility to ask questions after a presentation, and please use the Slido link that has been provided in the chat section of the GoToWebinar application. We will then read out the questions and Hugo will answer and conduct the discussion. So Hugo, over to you.
Okay, thank you very much for this introduction, and also thank you for thinking of me to give this webinar. It's an honor because It's for a young journal to be the one who kicks this off. So yes, so like I said, what I will be talking about is the topic of spin and angle resolved photoemission on topological materials. And I will, to a certain extent, I will be following what I've written also in the review article, but I will go in more depth at some points, and I will include some more recent results as well. So the outline of the talk, it's just it's here. I will give an introduction to spin and angle resolved photoemission spectroscopy, just a short introduction to topological materials. Then I primarily talk about spin interference and what is the result of this when we study topological insulators. And then I will give some change to topological semi-metals and related topics. So just to give a little bit before we get started, a little bit of background about me, where I'm now. You heard my CV, but I'm at the moment I'm at the EPFL here on the board of Lake Geneva, and we do our experiments actually pretty much on the other side of the country at the Paul Scherrer Institute, and this is displayed here. And here you see these donuts. This is the Swiss light source. Here in the forest is the Swiss FEL, the free electron laser. And this is all together with all the other facilities we have there. It's a first-class large-scale research facility. So besides studying topological materials, we do other things in the group, and I'll just give a very quick overview. The main topics are actually looking at spin orbitronics, looking at spintronics without magnetism. Then the part which I will be talking about today is how spin-orbit interaction can induce novel physical phases. And the third topic of our research in the group is actually that we use spin-orbit interaction, or the spin, as an extra tag in spectroscopy. An example of this is that you can actually measure the time scale of the photoemission process by measuring the spin, but this is not something I will talk about today. But common on all of this is the main technique, and which is spin and angle resolved photoemission spectroscopy. So it's a very quick review of what is angle resolved photoemission spectroscopy. It's a photon in, electron out technique. And if we measure the kinetic energy of the electron, then by energy conservation, given here, we can determine the binding energy of the electron in the material. By measuring the emission angle of the electron, we can, by momentum conservation, we can determine the momentum, the in-plane momentum of the electron in the crystal. And if we then plot it together, so light colors here are high intensity, dark colors are low intensity, you get a plot of binding energy versus momentum, and you measure, this is the band structure of copper, for example, and this is the calculated band structure, and you see the nice link between them. Then we can make cuts through it, like momentum distribution curves, energy distribution curves, or we can set ourselves at a given energy and scan all angles and get, for example, if the energy is a Fermi energy, we can get the Fermi surface. And altogether, with these kind of techniques, you can, like in an approximate way, see how electrons move in the crystal. So let's just discuss a bit more. What are actually the observables in photoemission? What I just said, okay, is something like the position of a peak, which gives us the band structure, the energy versus the momentum. But the position also, or actually variations in the position, actually give us the signature of many body interactions in the real part of the self-energy. The width of our peak gives us information about many body interactions, and through the imaginary part of the self-energy. The intensity of our peak gives us information about actually the orbital composition of our state, and I'll get back to that later as well. And then we have this, of course, on the background. And the last observable that we have is the spin. And when I'm talking about spin, I'm always talking in this talk, I'm talking about the spin polarization vector pointing somewhere in 3D space. And it's the expectation value of the ensemble of spin. We're not measuring the spin of a single electron, but of a beam of electrons which is emitted from the sample. So how do we actually get angle resolved photoemission than with spin resolution. A first approach, if somebody talks about spin and one wants to measure spin or separate spin up and spin down, would be, of course, to use a Stern-Gerlach type of analyzer, where as a function of applied magnetic field, you get this separation into the different angular momenta. Unfortunately, for electrons, this is not feasible because of the Lorentz forces on the electrons and the precision that would be required on the detector. So this is unfortunately not an option. So what would be another option? Would it, for example, to use circular dichrism? So you first come in with one light helicity, do your measurement, then you change the light helicity to the opposite sign, and you redo your measurement and you take the difference. There have been suggestions that this actually allows to measure the spin. There have been other suggestions that it actually is related to the orbital angular momentum, or others suggest that it's related to 2D confinement of the state. Here I have to say that the orbital angular momentum explanation is the best. It's long known that the light polarization only couples to the orbitals and does not couple to the spin. So one would get a signature of the orbital angular momentum, which in some cases, like this beautiful example here, actually is directly linked to the spin as well. But on top of it, one has to worry about the large influence of the experimental geometry. So this is not a technique to detect the spin of the photoelectron. Might be useful for other things, but not to measure the spin. So how do we measure the spin itself? And this is always based on some kind of spin selective electron scattering or reflection symmetry measurement. And there are three main approaches, which primarily differ by the energy at which they're used. So Mott scattering is at very high energies, spin polarized lead is at medium energies, and very low energy electron diffraction is at low energies. And the mechanism how they actually determine the spin. And I'll primarily talk about these two now quickly, and here there are other references to learn about split as well. So for V-lead, the idea is the following. If you have a magnetic material, so we have a magnetic target of which we let the electron scatter, we have our majority state or minority state, and if we now come in with an electron exactly at this energy here on the unoccupied edge of the bands, where only the majority states are possible, then only electrons with a spin parallel to the majority states can enter the sample. The others are reflected. So now by measuring the reflection of the electrons as a function of the magnetization of the target, we can say something about the spin polarization of the incoming beam of electrons. This is a very efficient technique with one problem, that you have to do it at relatively low energies. It requires a very clean surface, and there are some advantages, disadvantages, which I will not go into now. What we use is Mott scattering. Mott scattering, it's known already since, well, now almost 100 years, and it's based on actually on spin-orbit interaction, and that's the potential that an electron experiences around a nuclei is dependent on the spin of this electron. And I will not go too much in detail here of the mechanism, but this allows us, if we measure a scattering asymmetry, and we know the efficiency of our instrument, we can determine the polarization projected on some direction. So by using these Mott detectors, we have, or colleagues actually have made a analyzer or a complete detector or an instrument, which is called COFFEE, whereby COFFEE stands for the complete photoemission experiment, and we use it. We often go to the coffee machine to do our experiments, and again, it's so photon in from the synchrotron, electron out, it's momentum and energy filtered, and afterwards it's not detected, but it's accelerated again to 40 kilovolts, and with this high energy, it hits a gold foil, and then depending on the orbit it takes. So if it takes this orbit, it has a high probability to have a spin pointing into the screen. If it takes this orbit, it has a higher probability to have a spin pointing out of the screen. Now we measure this asymmetry between these two detectors. We learn something about the Z component. If we measure the asymmetry between these two, which we can do simultaneously, we learn something about the X component and so forth. Because the two detectors are placed 90 degrees with respect to each other, we get all three components at the same moment. And this is why we call it complete, because we have access to all the quantum numbers of the electron. So before now moving on to topology, I want to give some important aspects of important properties of spin and angle resolved photoemission that are often overlooked. The first is that all or almost all photoelectrons are highly spin polarized. It's very unlikely, and it doesn't happen very much also in practice, that you actually measure zero spin polarization. This might be that the polarization signal is too low to detect compared to the background if you have it, or that you actually have a magnetic sample where you average over different domains. But for the rest, almost all photoelectrons carry a spin. And what I'll be talking about today more is like that for non-spin degenerate bands, these measured spin polarization will always be 100% if one really measures a 3D component and takes the background into account. And I will get back to this at a later point. For spin degenerate states, actually you will also measure a spin polarization, and this is due to scattering and the spin orbit interaction that you have. And this I will not talk about today, but further information can be found at these papers. Another important property is that actually by using the spin as an extra tag in our measurements, so it's an extra observable that we have compared to normal ARPAs, we are able to enhance our resolution. And it's simulated here, and there's also much experimental data to support it. If we take, for example, peaks which have a width of 150 millivolts themselves, we can resolve a splitting of about 2 millivolts of this, even though the total energy resolution of the experiment might be 100 millivolts or something like that. And this is purely due to the addition of an extra observable. One other thing that if we're talking about spin, one has to take into account is actually the relation between spin and symmetry operations. So one symmetry that is very important for non-magnetic materials, and this is primarily what we'll be talking about today, is time reversal symmetry. So if I reverse the momentum, so I go from k to minus k, I also have to reverse the spin. And why is this called time reversal symmetry? It's like for angular momentum, if you look at it as a rotation, if I now reverse the time, the rotation goes the opposite way, so the spin reverses. Then the other aspect is the crystal symmetry. And when one thinks about the crystal symmetry and the influence of on the spin, one has to realize that spin is a pseudo vector. And what does that mean? That means that one has to invert the vector after a mirror operation. So it's illustrated here. This plane is a mirror. So if one takes this spin and one reflects it in the mirror plane, it's actually the vector itself would be pointing up. But now we have to invert it because it's a pseudo vector, and then it will point down. And same for this orientation. And the interesting part is now the spin pointing perpendicular to the mirror plane. So if we now mirror it like a classical vector, it would be pointing the opposite direction, but then we have to revert it and it will point in the same direction. And one example one sees directly from this is that at the mirror plane, only this purple spin would be allowed. It also allows to distinguish non-physical spin textures. For example, only for threefold, or not threefold, for odd rotational symmetry, an out-of-plane spin polarization is possible. If one takes, for example, the fourfold rotational symmetry, if one has out-of-plane spin pointing out of the screen here, one makes it a mirror operation to go here, then it would be pointing into the screen. Then one does again the mirror operation to go here, then it would be pointing out of the screen. But if I go from time reversal symmetry from here to here, then it should actually point into the screen. So this is now a conflict between two symmetries which cannot be resolved. So that's why this out of plane polarization is not allowed. And if you see it, it has nothing to do with the initial state spin texture. And another important concept that for non-magnetic materials are so-called time reversal invariant momenta. These are special places in reciprocal space where either my k factor is 0 or my k factor is exactly half a reciprocal lattice vector. And if we now put this in the time reversal idea, then we see that spin up and spin down have to be degenerate. And these are these special points where this has to happen. Okay, so now let's move on to topology. And I'm not a mathematician, I'm not a theorist, so my knowledge of topology is very limited. And I just know that topology has to do with the idea of objects which stay the same under continuous deformations. Then they have the same topology, and if one would have to make a non-continuous deformation, so for example cutting and gluing, it's a different topology. And an example is given here. We take a normal paper band or rubber band or something like that. If we now want to go to a Möbius strip, what we do, we cut it, we twist it, and we glue it back together, and then we get this idea. And those two have a different topology, and you cannot continuously deform one into the other. And this is also a nice example because this change in topology directly has very serious consequences. Here I have two surfaces and two edges, and actually here I have just one surface and one edge. So it's really showing that a different topological class can have profound differences, consequences. So another important idea is, and this follows from the rest, but the reverse of it, you can't transform one topological class into another without going through a singularity. And we'll see that if we actually at the interface between one topological class and another, we have to go through a singularity in between. So what does this have to do with band structures? And there I like to make the comparison to the real origin of the study of topology by Euler, and which is the Koenigsberg bridge problem. And it was the question in the time of Euler whether it's possible to in the city of Koenigsberg to cross all bridges of the city and cross them exactly once and come back to the same place from where you started. And this is something one can approach experimentally, of course, try all different paths and everything, but Euler showed it mathematically that this is not possible and is never possible at the moment that there's any region of the town which is connected to the other regions of the town by an odd number of bridges. So now what we can do is we can separate all towns in the world into two classes, either like Paris, where all regions are connected always by an even number of bridges. I'm not sure whether it's designed like this or it's coincidence, but and where an Euler route is possible, so you can cross all bridges and come back to the same place, and we call those towns trivial. Or you have towns like Koenigsberg, where this is not possible, and we call them non-trivial. And the same actually applies to band structures. One has these two possibilities in a first approach for insulators, that either you have a even or an odd number of band inversions, and this will be the difference between two topological classes. I will not explain how these band inversions and how these differences come about, but only what are the consequences of it. So if I now have a region with one topology and another topology, at the interface between them I have to go through a singularity. So this means that at the interface there is a state which must exist. And this is the topological protection that people often talk about. So how can you realize a topological protected band structure? How can you make sure that in a gap the state has to exist? In this case, it's clear I can change, make a continuous deformation, and I will just have a gap again, for example, here. In the case on the right, now I cannot make a continuous deformation to actually have no state crossing the gap. But here I still have to include the crystal symmetry. So for every state going to the right, I have to have a state going to the left. And if these states going to the right and to the left meet, then actually they can hybridize again and open up a gap. So the only way to avoid this from happening is if the states are spin polarized, because then time reversal symmetry at these time reversal invariant momenta dictates that they actually have to have the same energy for spin up and spin down. So they must cross. And this is actually what gives the so-called Dirac cone, if we zoom in here, which is then the signature of a topological insulator. So this is one way of looking at the problem. Another way of looking at the problem, and it's an old-fashioned way of looking at the problem, is from William Shockley. Well, it's actually more modern than the Euler way, is that if you close and reopen a gap as a function of some parameter, and here it's as a function of the parameter of the interatomic distance of a chain of copper atoms, you will have some in-gap states or some surface states. And you will get actually one state per band crossing and per surface or per edge. So now if we count the number of band crossings, then we actually have the number of states, and this is where the odd number of band inversions comes into play, to have an odd number of states, of spin polarized states that actually cross the gap. So now the main role of spin-orbit interaction in a 3D topological insulator is to keep this gap, so not the gap of the surface states, but the gap of the bulk states, to keep this open. Now, how actually these surface states look and what happened, this depends then on the exact shape of the band structure around this gap. It can be, this is the shape typically found for a topological insulator, but we can also have a gap which disperses with energy, or we can actually have a gap which is trivial and another topological gap further on. Now, if we expand this even further, then we see that every time that we have a band inversion, we need to have these states. But there are other things that can happen as well. So especially if you now consider what happens with spin-orbit interaction. So we can have no band inversion, then we have a trivial insulator. We can have a small band inversion and a very strong spin-orbit coupling, which is anisotropic, and we actually get a Dirac Semi-Metal. I will not talk about these today. You can have a band inversion and very small spin-orbit coupling, so you do not open up a gap. Then you get a nodal line semi-metal, or it's just because protected by symmetry, it's the same idea, and which is the closest to actually what Shockley was talking about for copper. Then you have the topological insulator where the gap is kept open, and then you can, on top of it, you can break your symmetries and everything, your crystal inversion symmetry, and then you get a wild semi-metal. I'll get back to that later. So first I will talk about topological insulators and then the Dirac cone, just very quickly. So this is one of the first observations of the spin texture of the Dirac cone. It actually one has to claim that we were the first to observe it, although many were working on it at the same time. Here we see this Dirac cone. Here we get this spin up, spin down when cutting through it, which directly illustrates there's only a single state actually crossing the Fermi level, and it has this helical spin one would expect. This data quality is absolutely below my standards, but it's good enough as a first measurement. And for us and many people around the world, the data quality has improved, and it's primarily because the sample quality and the understanding of the measurements have improved. And here's a more modern example for thin films of bismuth selenide, which is a topological insulator. And you see that the spin polarization is nice and smooth, and the cone is very intense and not fuzzy like here. But one thing that one always sees, and we have always seen, that the measured spin polarization, if we take the background into account, is always 100%. Although the calculated spin polarization, not calculated in a photoemission calculation, but for the initial state, it's 60%. So where does this come from, this difference? This is what I want to talk about now. And one thing we have to ask ourselves is whether the spin is still a good quantum number. I will not go through this calculation in detail out of time considerations, but this is just the Hamiltonian for the topological state, and one would get a spinors, but the problem is that these are not the operators for the real spin. They're actually related to the total angular momentum. So this is logical because we have spin-orbit interaction. So if we have spin-orbit interaction, we have to talk about the orbit and the spin together in a J. So one can also solve this problem now taking everything in basis of J and not in basis of spin, go through the same thing. One sees, okay, now we have to consider what is the orbital angular momentum. So here it's the p orbitals are split in the pz orbitals and the radial and tangential p orbitals. Then one goes through the same trick again, and one sees, okay, that now the eigenstates for this upper part of the cone, that the pz orbital is coupled to a clockwise spin, so let's say spin up. The radial orbital is also coupled to a clockwise spin, and the tangential orbital is coupled to a counterclockwise spin. And this is now the fact that the orbitals have a different spin coupled to it. This is just the result of spin-orbit coupling, and this is exactly what one would expect from spin-orbit coupling. There's an orbit and there's a spin coupled to it. So what are the consequences of this? One of the consequences is, of course, if one can probe the other orbitals, so whether one probes the tangential or the out-of-plane orbitals as a function of light polarization, one probes a different spin. And experimentally, this is shown here. It's again bismuth selenide as the example. Here it's for p-polarized light, we get down-up spin. For s-polarized light, we get up-down spin. So the spin helicity has reversed. And it's also nicely shown in this paper, which appeared around the same time. But again, the measured spin polarization is always 100%. And now it makes more sense because if I only measure one orbital, then I would have only one type of spin polarization, and all the electrons emitted have this spin polarization. Again, I say 100% if one takes the background into account, which is these fitted lines shown here. So, but there are further consequences actually of this effect, and that's shown here. So this is the spin polarization that one would expect. This is either the clockwise or counterclockwise. But now, if one does an experiment, one will see that there's also spin polarization in the plane perpendicular to it. And this will change as a function of photon energy. And the sum of all three of them, the factorial sum, will always be 1 again. And the origin for this lies in spin interference. The origin for having this other spin component, and also why it's also always 1. And this is what I would like to explain in the following slide. So again, we have this simple picture for bismuth selenide. We have the PZ and the radial orbits. They have a clockwise spin polarization, and the tangential orbitals, they have a counterclockwise spin polarization. Now, in a realistic experiment, I do not probe only one orbital. I probe a superposition of them. In the previous example, one could consider it, okay, what if the light polarization is between S and P? And I'll show an example of this afterwards. But in the general sense, it's just, okay, we cannot align our experiment that it's exactly like this, because we do not come in we come in with a given geometry and everything. So now we probe a coherent superposition of orbitals. So we automatically also probe a coherent superposition of spin states. And now one has to consider what happens if I make a coherent sum of spin states. This is that if one takes two spin states, sums them together, actually you get a spin which is in the plane perpendicular to it. And the direction along which it's pointing depends on the phase with which you sum them. One can, this simple exercise if you write down the spinors and then start summing them. So now what determines this phase? This phase is actually determined by the photoemission process and by the transition matrix elements. So it will depend on photon energy and on geometry in that sense. So if I now use two different photon energies, I see that the out of plane spin polarization, which is due to interference, has shifted sign, and this one could interpret, okay, that actually the phase has shifted with a factor of pi. Beautiful example of this using lasers, where it's very much easier to change the light polarization continuously compared to a synchrotron is given here. It's from the group of Shixin in Tokyo. Here, this is again the same idea. Different light polarization gives opposite spin polarization, but here on the right is the more interesting part. It's when if you continuously rotate the light polarization, you see that you continuously change the measured spin polarization. The blue one would be what one would call the clockwise and counterclockwise part, so clockwise, counterclockwise. And the red and the green one are are perpendicular to it. And you see if the blue one is 0, the red and green are maximum, and if the blue is maximum, the others are 0. And again, all together they sum up to 1. And this rotation, it's just like a sum the different components with different amplitudes instead of changing the phase. Okay, so these kind of effects, so this kind of spin interference effects, one would say, okay, how can I now link the measured spin polarization to the intrinsic spin polarization? It becomes very difficult. One advantage is actually you can use it, the change of intensity, in combination with this knowledge to determine what is the initial state spin polarization, and you get something like 70%, which is similar to the calculations. But it's also, one could say, okay, now the problem is, can I still trust my spin polarization that I measured? And yes, you can trust it. It is, but it's an effect of the initial state modulated with actually the effect of the photoemission process. And one would have to consider other things like actually the crystal symmetry and how the spin should change with the crystal symmetry to verify what you measure. Is it due to the to this interference, like is the case for bismuth selenide, and also the case of the famous example of the gold 111 surface state. Here's the spin polarization. You have an out of plane spin polarization, and this actually, if you rotate the sample, the spin polarization stays the same, and this completely is clear that this does not follow the crystal symmetry. So it means that it's all due, this out of plane spin polarization, due to the photoemission process itself. In contrast, here is a topological insulator lead bismuth telluride. Here, if you rotate the sample, you see that the out of plane spin polarization changes. It shifts sign, which is just, and it follows the crystal symmetry and the mirror symmetry, and that way you can say, okay, this is related to the initial state spin polarization. One example exactly where you have fourfold symmetry and you do have out of plane spin polarization is samarium hexaboride, which is said to be a topological condo insulator. And here, if you do spin resolved measurements, you actually do see nicely of this topological surface state, this spin polarization you expect. but you see on top of it this out of plane spin polarization, which is absolutely forbidden by the crystal symmetry because it's an even rotational symmetry. And so you know that this has to be due to interference, and this can be due to the really initial state spin polarization. For this, we just as a side remark, we see, although it's a strongly correlated system, it's a condor insulator, we see no signs of correlation in the spin structure. And this is on the 001 surface, and there's also been beautiful spin resolved results on the 111 surface, which verify this interpretation. Okay, so this is topological insulators from different kinds. And what I now want to do is move to some examples of Weil semi-metals. So here we have the example of a Dirac semi-metal, just the band inversion. And now we break the inversion symmetry and we get the generic band structure of Weil system. And these crossing points here, these are Weil points. And these Weil points, they, because of how the spin of the bulk states we're talking about here actually rotates around it, they are a source and a drain of Berry curvature. And this means that there has to be a surface state connecting them. So the reason for the surface state is similar to the example from Shockley that I gave, but that it has to actually go from source to drain, it is related to the Berry curvature. So let's look at an example of a Weil semi-metal. This is tantalum arsenide. The crystal structure has broken inversion symmetry. And if you measure it, then you clearly see here are you do not see it in this cut, one will have to make a cut perpendicular to it. Here are the Weil points, and this is this Fermi arc connecting them. One can measure again the spin texture of this Fermi arc. It's a combination of many measurements. Some examples of it are shown here. One has to fit really the bands to get the exact vectors that what one's looking at. And here one sees that actually the vectors are not nicely tangential to a constant energy surface, but they're just standing at some angle to it. And the reason for it is that here this is not around a time reversal invariant momentum. So, and it's only related to a mirror plane, which is here. That's the only constraint we have for the spin. Now getting lost, where's the mirror plane? I'm sorry about that. And this allows the spin to wind in a completely different way, and be pointing in this rather weird way. And this is also completely confirmed by or reproduced by density functional theory. One other thing one sees here, both in the experiment and in the DFT, is that there's another arc. So why are there two arcs? The second one is actually just a trivial arc, which happens to be there, and which happens to be there because there's another topological transition which is close by, which has not yet happened. And this is another important point to make, that actually the observation of a spin polarized surface state and an odd number of spin polarized surface state is a necessary but not sufficient condition for the identification of a topological state. If topological, you have to have a surface state, but there is possible also to have the surface state without being exactly in this topological phase. So one would also have to determine really that the Dirac or Weil points are present, or check for other perturbations. This sounds, of course, negative, because how do you now, it's more difficult to detect whether something is topological, but in practice, it means that you just want to know what's your response of your system, and this is independent of topology. So let me move on. So these were Weil fermions. We had the Dirac state, and now I just want to give a quick overview of what is in between, and those are so-called triple fermions. And so it's actually here at this point there are three states crossing here as well, and it's again protected by some symmetries of the crystal. There are two possibilities how these states are connected, either by just a single line or by 4 nodal lines. The experimental verification without spin resolution of just a single line is shown here for molybdenum phosphide. And what we said about is to find a set with actually 3 or the 4 nodal lines, and actually which to measure the spin of this triple fermion. And it's found in a system that we had been studying a lot before already, which is germanium telluride. It's a ferroelectric material. And here are some calculations. And here at these points, these are promising for actually to observe this triple point. Here it looks like you actually have 4 states crossing, but if you zoom in, like done here, it's actually one of the bands is split, the other band remains degenerate. And also here in this movie, it's shown how actually, if we go through this momentum range in very small steps, how actually this triple point forms. There's one that stays the same, and there's one that actually disperses out and comes back again. And this is this other nodal line that I was talking about. So this is confirms that it's a type B triple fermions in ferroelectric germanium telluride. Now, to measure them, one first has to find where in reciprocal space they are. For this one, scans the photon energy and does a lot of band structure maps and compares to theory, calculates what's the inner potential and everything. And then one finds energies where these triple points should be located. Verified this again. And then we performed spin resolved measurements around. And these are spin resolved measurements not of the surface states, but of the bulk states. And we see a clear spin polarization signal. Again, we go through our analysis and we can determine what is the spin winding of the states around this triple point. And we see it has actually a winding number of ±1. So when we go around it, it just winds once around it. And it's not that the spin makes an extra swirl when going around. There are other symmetries, again, that have to be observed. We see the time reversal symmetry is still observed, of course, and the Lorentz invariance is observed, which means that in the energy direction, the spin does not change if one goes above and below the triple point. And another interesting thing is, which was not clear before, is that the 2 triple points at different sides of the Brillouin zone, they actually have the same spin texture. And it's not that it's reversed between them. There's actually now recently there's a whole flurry of wild states that come out, and I will just go very quickly. It's based especially in chiral crystals. You can have states where 4 states cross, or 6 which have Berry or Chern numbers of -4 and +4. So one would expect the surface states to go really from that one to that one, which makes them very large. You see a signature of the chirality of this. But on top of it, of all these wild points that you have in chiral crystals, you also have the most simple wild point, which is just a single one. Normally wild points come always in pairs, but if we break this mirror symmetry, it's possible to have only one of them. And again, here we verified by verifying the spin texture that it's really a single wild point, and that you can find it in this material platinum gallium. And this brings me to the very last example of another topological system, and this is our so-called higher order topological insulators. Everything we talked about before, we are looking for 2D surface states on a 3D crystal. But there's also the possibility for systems that are trivial in this aspect, but if you look in a second order approach, that you actually see that you have 1D surface states or hinge states at certain edges. And the clearest example of this is elemental bismuth. So here are the calculations on these hinges. One should expect 1D topological states. This is then STM on it, and one sees, okay, on these hinges one has higher density of states, So there are 1D states located there. Before that, before this prediction, it had already been shown on islands with harpers and spin-resolved harpers that you do have these spin-polarized states. The problem here was, okay, you have only one state somewhere, you cannot control them. And actually, we realized that we did the killer experiment already 12 years ago or 13 years ago, where we actually made a regular array of these edges of bismuth by looking at bismuth 114, where one has all these edges. And then if you do photoemission, you actually average out over all of them, and they all have the same thing, and you have a high enough signal. Yeah, this is their one-dimensional signature. And if when we measured the spin of it, we clearly saw this spin polarization and this Dirac. And we explain it at that moment again by a one-dimensional edge states on an n-dimensional bulk state. Okay, so this brings me to the end, and I just want to end with one warning. So topology is abundant. It's actually for insulators. You either have a trivial insulator or a topological insulator, and there's about 2 times as many trivial insulators as topological insulators. But if you look at metals or semi-metals, it turns out that pretty much all materials are topological in one way or the other, and especially if we include this higher order topology. So this brings the question, what is a normal or trivial metal? It's a question to which I do not yet have an answer. My speculation might be that it's just elemental sodium could be. And it also means the following, that although topological classification is very, very useful and a beautiful concept, it does not mean that if something is topologically non-trivial, that it is of high specific interest. And with this, I finish, especially just the people who have been doing all the work in the group. Well, I'm enjoying the mountains, and I would like to leave you with the last remark that spin and angle resolved photoemission is a powerful tool for the identification of spin texture in topological materials. That for correct interpretation, spin interference has to be taken into account. And as the last message, that actually non-trivial topology is abundant in semi-metals. And with this, I thank you for your attention, and I'm looking forward to many questions.
Thank you very much, Hugo, for this really fascinating talk. And you showed us clearly the richness of the research in this area, which we have witnessed over the last few years. I would like to remind the audience to use the link provided in the webinar application to pose any questions you have to the speaker. So we can open now the question and answer session, and I'll read a couple of questions that we have already received. The first question is very general in nature, but also very, very interesting. It reads, where do you see both your research focus and this field more generally heading in the future?
Okay, this is certainly an interesting question, and it's of course one that I've thought about many times. For me, my research interest is focused on using the technique of spin and angle resolved photoemission to learn completely new things, might unexpected. One example of this is like that, where you can use it to actually get the intrinsic time scale of the photoemission process. Other examples of it is actually we can use it to distinguish spin singlet and spin triplet states for superconductors, or we can in future experiments maybe be able to look at antiferromagnetic fluctuations and those kind of things. This is my personal interest in research and drive, which is based on the technique, on the development of it, and looking for new shores actually to use it. if I consider the fields of topological materials, I think at this point, one of the things one has to go through to is actually start using them. So we have spent the last decade or more than a decade to classify them, to identify examples, to really understand what is happening in their band structure. And so the next point would be, okay, make devices, and then one could say, what can we learn again with spin and or photoemission or other techniques to optimize these devices? And for me, the field has reached this point. Okay, it needs to go beyond pure identification to actually use of it. So I hope this answers the question.
Thank you. We have more questions coming in. I take now one question which is more technical in nature. What are the challenges using a MOT detector?
What are the challenges using a MOT detector? The main challenge is that the experiment is, or the MOT detector is at high voltage. So typically one talks about 40 kilovolts or something like this. And so this means that the detection signal coming out, you cannot directly connect to your computer, unless you want to have your computer also at 40 kilovolts, of course. So you need to somehow screen it from the rest, and this we do with optical output. But it also means that if there's something wrong during the measurements, actually you cannot quickly tune something or that kind of stuff. This makes it challenging. It's primarily the high voltage. Another thing which makes it challenging is actually the low efficiency of it. Let me see if I can go through it. But this is something we're working on, and we're actually developing new kinds of MOT detectors, and there's also other developments going on by other groups to enhance the efficiency, because one of the challenges is the low efficiency. So it takes a long time, several hours, to measure these kind of spin resolved spectra. And one way to resolve this issue that we decided is okay to go to multiplexing. So instead of just getting for every point in reciprocal space one by one, we actually developed a experiment where we can measure it all at the same time. And it's now under commissioning. And this is an example of during the commissioning, it would be energy would be along this axis and angle along this axis, and you would in one shot get the full spin polarized band structure from this. Here, this is just a grid for calibration. We see already that some we can measure the asymmetries. It's something that we're working on now. There are also other approaches to enhance the efficiency, and this, for example, with this V-lead, it's said to be more efficient, but our experience is that it's only slightly more efficient. So high voltage, low efficiency are the main problems in working with these kind of systems.
Thank you. The next question: how to judge and establish the relationships between spin and topology quickly? Symmetry ?
Yes, symmetry is always a very important thing. So the connection between topology and spin is relatively simple in that direction. If you have a topological system, you can consider what would be the spin texture you would expect from it. The other way around, if you measure some spin texture and then to go to the topology from that, can sometimes be more involved because you can have other effects which change the spin texture. But the easiest way is, of course, symmetry considerations. Does it make sense what you measured? How does it respond to symmetry? Or, this is always a good approach, how does it compare to what theory tells you how it should look? And this is often one of the quickest way. So there's a one-to-one connection between spin and topology when going from topology to spin, but unfortunately it does not work one-to-one in the opposite direction. But symmetry helps a lot.
Thank you. The next one, can you elaborate on how to calculate spin interference effects?
Yes. So let me just go to the relevant slide again. Sorry. No. There. So just to explain it again a bit. So we have, these are our spinors. And we say, okay, the expected spin is along the y direction. This is what the initial state spin polarization is. And we have this combination of plus y, clockwise, and counterclockwise. So now if I sum these two spinors together, so plus y, if we write it in the basis of y, is as a spinor is a vector of 1, 0. Minus y is a vector 0, 1. So if I sum them together, 1, 0 plus 0, 1, I get a vector 1, 1. This is actually the spin along the x direction. This is the spinor, the eigenspinor for the x direction in this basis. So this means if I sum a spinor y plus y and minus y coherently, I actually get a spin in the x direction. Now, if I sum it with a phase term, so a phase which is different from 0, as illustrated here, so 1, 0 and 0, 1, then the 0, 1 becomes 0i, I get 1i as a vector. 1i is actually the eigenspinor in this basis along the z direction. So this means that if I sum them with a phase shift of 1/2 pi, I actually get a spin along the z direction. If I now take a phase shift of pi, then I get the minus x direction. If I get the phase shift of 3/2 pi, I get the minus z direction. And I get everything in between if I sum them with different with phases in between. And it's just the spin rotates in this plane as a function of the phase with which I sum them together. So this is the idea behind spin interference of the phase. If now on top of it, if I say I keep a fixed phase, but I change the prefactors, so the amplitudes of the different spinors, then if this one has amplitude 1, this one has amplitude 0, then I get actually only 1, 0, and I keep plus y. If they have the same amplitude, I get something like again around x, and if I have something like 2/3 of this and 1/3 of this, I get 1/3 along the y direction, and I get 2/3 along the x direction. There, my summation is not exact, of course, so there's a geometrical normalization that I missed in this quick example. So I hope that explains the idea of spin interference. It becomes clear if you write down the spinors in their basic vectors.
Thank you. I don't see any further questions in the Slido, but maybe I can ask one myself. In the end, you made a rather provocative question: what is a normal metal? And to me, that sounded like a challenge to the theory community to have another look at these boring materials, so to speak. And you indicated in your earlier presentation that normal DFT seems to work quite well once you do it properly and thoroughly.
Yes.
perhaps one can then interpret your comments is that there is a huge demand for systematic mapping of the metal band structures with the DFT type calculations and their band structures in detail to unravel the phenomena that you described.
This is exactly what's done in this paper in this Topological Quantum Chemistry website. This actually, they did a course overview and then refinement for all known materials.
Okay, I see. Thank you.
But my challenge to theorists, yes, still remains. But what is a normal metal?
Okay, I get you. Yes.
And maybe one could say doped silicon is a normal metal, but I'm pretty sure if you look somewhere in the silicon band structure, one might also find some topological features. But I do not know, of course.
Yeah.
And but that challenge remains because what one would think of as a normal metal, like copper, is actually a nodal line semi-metal. Of course, metallic hydrogen, I think, would be a normal metal.
Okay.
That's it. Unfortunately, we cannot measure that with photoemission.
Okay, so there are no further questions. So once again, Hugo, thank you very much for your fantastic presentation.
Thank you.
I'm looking forward to learning more of your really intriguing and fascinating results. And with this, I would like to thank all the attendees and close the webinar. Thank you very much.
Thank you. And thanks everybody for listening.